Okay, from our previous video we looked at part A and we introduced part B of this question, and we're interested in the rate at which the radiant measure of the angle, so the size of this angle measured in radians, and this angle is defined by the pole and the horizontal between the bottom of the pole and the wall, there and there. So as that angle, we want to know, well, what rate is that changing as the base of the pole slips out from the ground and travels at some known constant rate of maybe a meters per second. It could be any, it could be 2 meters per second, it could be 3 meters per second. So d theta dt, the rate of change of the angle, is what we were trying to find. Now that depends on the distance at which the base of the ladder is away from the wall, which is defined as x from the previous video. And as this moves out at that speed, x increases, and as x increases and gets bigger and bigger and bigger, then the angle will decrease. So we've got a related rate of change there. So d theta dt is equal to d theta on dx times dx dt, for it to all relate and be connected and equivalent. So we need to now identify, to work out the rate of change, we need to identify what is d theta dx. You know what dx dt is, the rate at which it moves away from the wall is a meters per second, given by this bit of information. The lower end of the pole moves away from the wall at a constant speed, moving away from the wall at a constant speed of a meters per second. So what is d theta dx? So I need to think about my object here, right angle triangle, sum theta, where I have x as my unknown amount. Okay, so, and my ladder is 5 meters. What's the relationship that we have here between this side of the triangle and the hypotenuse? Well, I have to draw my trigonometry. What do I know? I know that cos of the angle is equal to the adjacent side of the triangle, which is this side of the triangle. The adjacent is the side next to the angle, over the hypotenuse, 5 meters. Okay? So I have an expression here that I'm going to have in terms of x. 5 cos of theta. Now, I need to be able to, from this, work out what is d theta dx. Well, that means I need to have theta as my independent variable, and I need to have x as my dependent variable. But I have it the other way around. I have x as my dependent variable and theta as my independent variable. Well, that's tricky. But one useful thing we need to remember is I'm going to draw on the fact that d theta dx is really the reciprocal of dx d theta. The derivatives between the two are just reciprocal relationships, because if I just think of these as a fraction, if I do 1 divide a fraction, then multiplying by the reciprocal, I'm just going to flip the fraction upside down. The numerator becomes denominator, denominator becomes numerator. So if I work out dx d theta from this given rule here, and I put it in a denominator, made a reciprocal, I'm going to get this expression. So, therefore, dx d theta is the derivative of cos of the angle, and differentiate that with respect to the angle. So, what is the derivative of cos? Anyone remember? Maybe? Candace? What is it? It's minus sine. Good girl. Well done. I can see you've been studying. Very proud. Please keep it up. So I'm going to have 5 times the minus sine of theta. Okay? Now, that means the theta dx is 1 on that. Sine of theta. Alright. Good. Let's see how that's going to work out with the rest of the problem. Now, put that together with my rule. Therefore, d theta dt, the rate of change, is going to be d theta dx, which is what I've got here, minus 1 over 5 times sine of theta, multiplied by dx dt, which is the rate at which the base of the pole is moving away from the floor, which is a. Okay, and I get this expression. A over 5 times sine of theta. Okay? Now I don't have an actual value yet. I don't have a rule, a numerical value that I've in its simplest form. I need to try and figure out, well, what angle do I get? What angle do I get at the instant that the question's about? And I have to come back to information. I need to find this rate for the instant that the foot of the pole is 3 meters from the wall. 3 meters from the wall is somewhere over here. The situation is where we have some angle theta for a pole that is 5 meters long and it has to be 3 meters away from the wall. What angle do I get? Got to use some trigonometry to help find that. So I have now a nice problem where we have I have, because of the relationship perhaps being some adjacent end, but maybe I can work out a value over here to get the opposite side, because I know the sine of the angle times 5 is the same as the opposite side, and cos of the angle times 5 gives me my adjacent side, which is I know already. If I've got sine of the angle here, I want to be able to replace that with a value. So I want to know, well, what is sine of the angle for this right angle triangle? I need to know what my opposite length is, since sine of the angle is the opposite side of the triangle over the hypotenuse. How am I going to get a value here? What do you think I need to do? Maybe Pythagoras theorem might come into play. Okay, so using that rule, I will have my opposite side, let's just call it b for a quick symbol. I'll have b squared will be c squared, 5 squared is 25, minus this side squared, which is 9, and that gives me 16. So b squared is equal to 16. I like that number. B must be equal to 4. This is a nice right angle triangle. It's called a Pythagorean triad. 3, 4, 5. They're good. Nice and friendly. So the opposite side must equal to 5. And that means then I've got an expression 4 over 5, which is my equivalent to sine of the theta. Nice little thing I can replace sine of theta with. So that means I'll have negative a over 5 times 4 over 5. 5 times 4 over 5, well, the 5's cancel, and I just get negative a over 4 radians per second, not meters, radians per second. Because we're doing an angle. There's our rate. Again, all dependent on what this number is, on how fast the foot of the ladder falls and moves away from the side of the wall. It's going to affect the rate at which the top of the ladder drops down the wall, and it's going to affect the rate of this angle decreasing and decreasing. Alright, very interesting problems, and this is the scope of applications of circular functions that we need to work towards to get ready for our exam. So we've got a little bit of practice and some homework to do. What do you reckon?